Hello and welcome to the lecture on special theory of relativity. This is Einstein's special theory of relativity, and this is our first of two chapters covering Einstein's two theories of relativity, the second theory being the general theory of relativity. The special theory came first. It is special because it is more specific and less encompassing than the general theory of relativity. Okay? So this is the simpler theory if you'll indulge that idea. Okay? So we're going to kind of start where relativity comes in, why we needed to have the special theory of relativity. Then we'll, of course, talk about its consequences that are both strange and amazing, and how their real-life consequences are actually backed up by plenty of experimentation and just have real-life consequences. All right. Okay, so we'll talk about motion is relative. This is the more classical notion. Then on to the two postulates of the special theory of relativity. Then we'll start off with something that we could finish on, but we'll start with it, and that's simultaneity. How the special theory of relativity means that things that were assumed to be just the nature of the universe, in fact, aren't. Okay? And then we'll get into the space-time and some of the most well-known consequences of special relativity, which are time dilation and length contraction, with some specific ideas in between. Then we'll talk about how the special theory of relativity actually leads to the well-known theory E equals mc squared. Although it might not seem directly related, it is, and that's because of something called relativistic momentum, which then relates to relativistic mass and energy. And then finally, we'll finish off with the correspondence principle. All right, so let's start. Motion is relative. The place from which motion observed and measured is a frame of reference. That's the technical term for it. An object may have different velocities relative to different frames of reference. So you are at rest relative to your chair, if you're sitting in a chair, but you are in motion relative to the sun because the Earth is in orbit around the sun. So that's a case of relative velocity. 0 in one reference frame, definitely not 0, about 10,000 kilometers per second or 10,000 meters per second, 10 kilometers per second in another reference frame, the orbital reference frame. Okay? So to measure the speed of an object, we first choose a frame of reference and pretend that we are in that frame of reference standing still. Then we measure the speed in which the object moves relative to us. So we're an imaginary observer. That is relative to the frame of reference. Isn't there some reference frame that is absolutely still? Isn't space itself still, and can't measurements be made relative to still space? So this is a big question, right? Is there some ultimate reference frame, some fundamental reference frame, which is the true reference frame of the universe? Now, the simple answer is no. There is no absolute reference frame. But for a long time, up until the turn of the 20th century, scientists, astronomers thought that there might be, okay? So that led to a famous experiment called Michelson's interferometer. And in this experiment, a beam of light from a monochromatic source was separated into two beams with paths at right angles to each other. These were reflected and recombined to show whether there was any difference in average speed over the two back and forth paths, all right? The interferometer was set with one path parallel to the motion of Earth in its orbit. So that's the fast speed of Earth racing around the sun, and the other perpendicular to that orbit. Either Michelson or Morley carefully watched, as the people who did the experiment, for any changes in the average speed as the apparatus was rotated to put the other path parallel to the motion of Earth. But no changes were observed. Okay? Now, the reason they were expecting a change is because there should have been a different change in the path of light relative to this idea of an absolute reference frame. And the absolute reference frame was known as the ether. That was the kind of the placeholder name that scientists gave to this kind of like background existence, space itself. And everything, Earth, the sun, moved through this fixed reference frame. But if that was the case, if that was the case, then the light should have been affected by the relative motion of Earth. Now, we knew, and at the turn of the 20th century, Michelson and Morley certainly knew that light was much faster than Earth's orbit around the sun, but Earth's orbit around the sun was fast enough that there would have been a measurable difference using this precise measurement of light. Well, but there wasn't. So that meant that there was no absolute reference frame. And this set the stage for a whole revolution in physics. Because if there was no absolute reference frame, then what kind of universe did we live in? And this led to some big questions about light, okay? And one of the people that was thinking about these big questions about light was Einstein. who was very intimately familiar with the results of Michelson's and Morley's experiment. And he realized that perhaps it was light itself that was the absolute. And that's why there was no measurable difference. But if that was the case, if light, a traveling phenomenon, was the absolute of the universe, then there must be something else that wasn't absolute, which was space and time itself. And that was a weird idea that many people would never have considered. But great minds will entertain strange ideas and follow them to their natural conclusion. And that is what Einstein did. So let's consider his postulates. All the laws of nature are the same in all uniformly moving frames of reference. Now this had been assumed for a long time, but Einstein wanted to build on this idea. And the laws of nature, by the way, would include, of course, Newton's laws of motion, universal gravitation, but they would also include all the laws of electromagnetism, Maxwell's equation, Faraday's law, right? Of course, Maxwell's equations include Faraday's law, but some of these, the ones that you may remember from previous lectures, Ampere's law, Ohm's law, right? Anything that involves the movement of electrons and the propagation of an electromagnetic field, which of course is light, okay? So, electromagnetic induction, great example, that should behave the same in any reference frame, no matter how fast you're moving. Fundamental physics shouldn't be affected just by your motion, because if that was the case, then we couldn't live in a universe where there was stars racing at high speeds and interstellar gas condensing at high speed and all these processes, because there'd have to be different physics for all the different velocities. And that's not what we see. We see that the models match and the observations match a universe where the laws are universal no matter how fast you're moving. Okay, so that's the first postulate. The second postulate was very much a consequence of the idea of the Michelson's and Morley experiment. And that was that the speed of light was always the same, regardless of the motion. There was one speed of light and it was a constant. Okay. You might be like, oh yeah, speed of light's constant, sure. But think about how weird that is. Because that means that if you're going at 99% of the speed of light, and you look at light, you'll see it going at the speed of light. You won't see it going at 1% the speed of light, because you can never catch up with it. But if you can never catch up with light, then how is that even possible? How is it that you can never catch up with something? How is it that when you're going almost the speed of something, you don't see it going side by side, but instead you see it racing past you? That doesn't make sense, right? That requires something fundamentally different about space, because the only way that the light can be racing past you, if you're going nearly as fast as it, is for it to be traveling through a different space than you. Okay? What does that mean then? What does it mean then to have space and time affected by this postulate? Well, that's what special relativity is all about. It's about the non-permanence, the fact that space and time are, you guessed it, relative, hence the name. Okay? So, one of the first big consequences of this way of thinking, this theory that Einstein proposed, was simultaneity, the effect on simultaneity. So, we say that two events are simultaneous if they occur at the same time. Two events that are simultaneous in one frame of reference need not be simultaneous in a frame moving relative to the first frame. Now, this is a big deal. So we could have two sensors that go off in a moving reference frame, but in a rest reference frame, or at least, much slower reference frame relative to the moving one, those sensors may appear to go one first and then the other. And I guess I shouldn't say appear, because they actually don't occur at the same time. So now we have the idea that simultaneity is relative. Two events that are simultaneous in one reference frame truly are not in another. And that's all because of the two postulates. Okay? So let's explore this idea with what's called a thought experiment. So from the point of view of an observer who's traveling within a compartment and moving very fast, because in all these cases we have to be moving fast enough that we're some large fraction of the speed of light so that the effects would be noticeable, okay? Light from the source travels equal distance to both ends of the compartment and therefore strikes both ends simultaneously, okay? So the two events are the simultaneous striking of the light on either sides of the compartment. However, For an observer on the ground, all right, the events of light striking the front and the back of the compartment are not simultaneous from the point of view of an observer in a different frame of reference, right? Because of the ship's motion, light that strikes the back of the compartment doesn't have as far to go, and strikes sooner than light that strikes the front of the compartment, okay? And that's because the light travels at the same speed in every reference frame. The speed of light is, the velocity is the speed of light, which is represented by the letter c in both reference frames. That's what ties them together. And that's what makes for this consequence. Because if there was anything else, like a bullet that was traveling, then they would agree on simultaneity. But if it's light, then the two observers will not agree on the simultaneity. They fundamentally will see different phenomena. Okay? All right. So that's one of the big consequences of light traveling at the same speed in every reference frame. Now we live in a universe where things are truly relative. Okay? At least events happening at the same time. Okay. Well, let's talk about the other consequences. And to do so, let's lay the groundwork of understanding what space-time is. So space and time are intimately linked together. Things exist in space-time. They don't just exist in time, nor do they just exist in space. And space would be up, down, left, right, back, forth. Okay, X, Y, Z. Time is measured, by the variable t, right? Represented by the variable t. It's time. It's the passage of time. Okay. So each object, each person, each planet, each star, each galaxy has a space-time coordinate, and it exists in the space-time continuum. Okay? One observer's measurement of space and time differs from the measurement of another observer in some other realm of space-time in such a way that each observer will always measure the same ratio of space and time for light. The greater the measurement in distance in space, the greater the measurement interval of time. Okay? Because the ratio of space over time must always be the same. So if your space is expanded because of your relative motion, okay, then your time is expanded accordingly. All right. So that's the interesting idea about space and time, because the ratio must always be c, because c, the speed of light, photons, represents something universal about the universe. Okay, so is the non-simultaneity of hearing thunder after seeing lightning similar to relativistic non-simultaneity? Is it about things traveling near the speed of light? Is it about the light traveling, right? Is it? No. Okay, it's a completely different phenomenon. It's just because there's two signals, there's the light signal and the sound signal, and those travel at different velocities. So totally different phenomenon, not the same thing at all. Suppose that the observer standing on a planet sees a pair of lightning bolts simultaneously strike the front and rear ends of the compartment of a high-speed rocket ship. Will the lightning strikes be simultaneous to an observer in the middle of the compartment in the rocket ship? Okay? So someone on the planet sees them strike simultaneously. So, before we had an event that was happening from the point of view of someone in the rocket ship, and it was simultaneous, and someone on the ground said, no, it wasn't, okay? And it wasn't in their reference frame. Does it work the other way? Could it be simultaneous in the person on the ground's reference frame, and then non-simultaneous in the person in the rocket ship? Well, yes, of course, okay? So, absolutely. And so the answer here is no, because it was asking, will they be simultaneous? So no, they won't, because the lack of simultaneity goes both ways. There's nothing special about a slower reference frame versus a fast reference frame. It's just that something that is simultaneous in one reference frame will not be in another. And sometimes that difference in simultaneity is so small because the velocities are so much smaller than the speed of light, in which case the effect is negligible. But if the velocities are close to the speed of light, then it becomes noticeable. All right, so continuous spacetime, time dilation. Okay. So imagine that we are somehow able to observe a flash of light bouncing to and fro between a pair of parallel mirrors, like a ball bouncing to and fro between the floor and the ceiling, right? And then we can measure it because there's something that triggers in each mirror. So we can kind of tell how quickly it's bouncing back and forth. If the distance between the mirrors is fixed, then the arrangement constitutes a light clock. That's a term given to this type of measurement, which is really helpful for understanding special relativity. Because the back and forth trips of the flash take equal time intervals, right? We'll always take the same amount of time because it's the same distance, right? Okay, makes sense, totally makes sense. And the speed of light is constant. Okay, good start, right? All right, so now let's think about how time is not the same in different reference frames. We basically have the same kind of thought experiment. We have someone in a fast compartment and we have someone on the ground, okay? So an observer moving with the spaceship observes the light flash moving vertically between the mirrors of the light clock. Okay, right? So their path is this path here, all right? So one half of the back and forth motion would be h. An observer who sees the moving ship pass by sees the flash moving along a diagonal path. So now we have d, which is greater than h, okay? So for this observer, the path is longer, okay? Well, what must have happened then? Because the light is moving at the same speed for both the observer on the ground and the observer in the ship, but the distances are different. The paths are fundamentally different, but yet the speed is the same. So if the paths have differed, but the speed hasn't, then something else had to change. What was it? It was the time, okay? So suppose now that we are standing on things quite different from our reference frame, for we do not see the light path as being simply up and down motion, because each flash moves horizontally while it moves vertically between the two mirrors. That's from the point of view of the person on the ground reference frame. We see the flash follow a diagonal path, as we said. Because the speed of light is the same, there's the postulate, okay? In all reference frames, the flash must travel for a correspondingly longer time between the mirrors in our, that's the Earth-based, frame than in the reference frame of the onboard observer, okay? So in other words, since the distance got bigger, the time must have got bigger as well. The time stretched out. The relationship between the time, this t0 is called the proper time, in the frame of reference moving with the clock, and the time t measured in any other reference frame, in this case, a reference frame of someone standing on the ground, moving much slower than the ship, we call that, which is called the relative time, the relationship between the two is represented by the following formula. And this is a formula you're going to be responsible for. Now, the derivation, the postulate is all earth-shattering, amazing, high-level physics. But we can see the equation is actually quite manageable. It's simply that the relative time is equal to the proper time. And proper time is tough to get your head around at first. Proper time is always this. It's always in the reference frame where the two events are simultaneous, okay? And the events here is in this case, it's where the two events occur at the same location. And the events would be sending the light from the bottom and then receiving the reflected light back at the bottom. Those would be the two events. And as long as those events occur at the same place, then that's the place where proper time is measured. And the only reference frame where those two events occur at the same space-time coordinates is in the spaceship, okay? All right. And so then we would have this equation, which is 1 over the square root of 1 minus the velocity of the spaceship relative to the other reference frame. So v here just represents the relative velocities between the two reference frame, and then the absolute speed of light, c. All right? And c is 3 times 10 to the 8 meters per second. All right? And so we can simplify this and call the whole 1 over the square root of 1 minus v squared over c squared, we call that the Lorentz factor represented by the letter gamma. And then we can rewrite it like this, which is really nice because that when we compare it to length contraction, it's nice to see that here we have a time dilation. So in other words, t is always going to be greater than t0, okay? So the relative time is greater than the proper time. That's why it's dilation. Just like your eyes get dilated, this is a lengthening of time. Okay? All right, so as the speed of the spaceship increases, the Lorentz factor increases as per this graph. And this is this particular type of function. When you graph a 1 over the square root of 1 minus the ratio of values squared, you get this graph that at first almost stays completely horizontal, as you can see, and then really quickly asymptotically approaches. All right? So it shoots up to infinity as we get closer and closer to c. The clocks will tick slower and slower as the spaceship approaches the speed of light. And what clock will tick slower and slower? The relative clock on the spaceship. So in other words, time will pass slower and slower on the spaceship relative to the ground-based observer as the spaceship approaches the speed of light. All right? So when we see the rocket traveling at close to the maximum rate through space, the maximum rate being the speed of light, we see its time practically standing still. So any time-dependent phenomenon on the spaceship would be almost completely stopped. All right? So if somehow it was a glass spaceship and you could like see someone walking, you'd see them walking really slow. If you could see their heart beating, you would see their heart beating incredibly slow, like 1 beat per hour or something, because time would be stretched out. We'd see that. Now, if then the person in the spaceship, right, if we go back to their frame of reference, is time running slow for them? Absolutely not. Absolutely not. Time is not running slow for them at all. Time is running at a normal rate, okay? How would they see the passage of time for people on Earth? Well, they'd see it moving at a very fast rate. They would see time racing ahead. So they would see hours go by for every 1 second of their time, okay? All right, now we don't have people traveling at near the speed of light, but there are things that do travel at near the speed of light, and this phenomenon is real, by the way. This isn't just fantasy. Okay, so if you were moving in a spaceship at a high speed relative to Earth, would you notice a difference in your pulse rate or the pulse rate of people on Earth? Okay, you would notice a difference in the pulse rate of people on Earth. They would be running faster, but yours wouldn't. Okay. So while observers A and B agree on measurements of time, if A moves at half the speed of light relative to B, then, right, or will observers A and B agree on measurements of time? Okay, so will they if one is moving half the speed of light? No, they'll disagree completely. Okay, half the speed is big enough to have an effect. If we look at the graph, we can clearly see that once we reach half the speed of light, we have a noticeable effect in the gamma factor. Okay, the gamma factor is about 1.2. All right, and that's enough to be measurable. Okay, so they would not agree. Will observers A and B agree on measurements of time and if both A and B move together at half the speed of light relative to Earth? Yeah, they would. Okay, because they'd both be moving at the same speed. If there's no relative speed, there's no v. Then there's no Lorentz factor. There's no time dilation. There's no stretching of time. You need relative velocities to have a stretching of time. Okay? Does time dilation mean, that time really passes more slowly in the moving system, or that it only seems to pass more slowly? Okay? It's good, because think about what I said about simultaneity. It's not that things appear to not be simultaneous, it's that they're truly not simultaneous. So you can guess, the answer is it really passes more slowly, right? It's not just a perception, it's not just a trick of observation, right? It really is, because time is relative, it is not absolute. In order for the speed of light to be absolute, time must not be. And that's what we see, that's the universe we live in. And that's not what we would think, right, from our everyday experiences, leading up, from early humanities, building civilizations and passing through, eras of great enlightenment, throughout those civilizations and moving to the modern era of technology. We never would have thought that time is relative. There was no indication of that until we started to wonder about the ether and did experiments to show that the velocity of light is the absolute. And that changed everything, okay? Time is relative. It really passes more slowly in moving systems. All right, so a really interesting consequence of this is the twin trip. Okay, it's a fun thing to think about. Identical twins, one an astronaut who takes a high-speed round-trip journey in the galaxy while the other stays home on Earth. Okay? When the traveling twin returns, he is younger than the stay-at-home twin. How much younger depends on the relative speeds involved. Okay? So we have the idea that one twin leaves, right? So they're the same age when they leave, okay? And then one takes off and then comes back. When the person comes back, they're about the same age, not that much time has passed, but a huge amount of time has passed for the other twin, okay? So the reason this works is because of the relative passage of time. Since motion is relative, why doesn't the effect work equally well the other way around? Why wouldn't the traveling twin return to find his stay-at-home twin younger than himself, right? Because it seems like there almost seems to be this fixed nature, like the person that stayed slower has to be the older one. Why is that? Well, it has to do with the turning around of the other twin. The fact that the twin that goes on the trip experiences two separate reference frames. One moving reference frame away from the stationary twin, and then one moving reference frame towards the stationary twin. And those two effects, they're not equal, and what happens is that we end up with them younger. But it requires them turning around. If they don't turn around, the twin effect doesn't work. Which is sometimes why it's called the twin paradox, because it seems to contradict relativity. Because relativity says, oh, well, everything's relative to one reference frame. Well, then this is saying there's something special about the rest reference frame because they're the only ones that get older. Well, there's nothing special about the rest reference frame. Again, it's only because the traveling twin experiences two separate reference frames. One way to think about that is to say when no motion is involved, the light flashes are received as frequently as the spaceship sends them. Okay? When the sender moves towards the receiver, the flashes are seen more frequently. And when the sender moves away from the receiver, the flashes are spaced further apart and are seen less frequently. Thus, okay, suppose the traveling twin recedes from the earthbound twin at the same high speed for 1 hour, and then quickly turns around and returns in 1 hour. Following this line of reasoning, with the help of the figures, okay, the ones that we just showed, the traveling twin takes a round trip of 2 hours, according to the clocks aboard their spaceship, including their biological clock, right? How much they age. This trip will not be seen to take 2 hours from the Earth frame of reference, however. As the ship recedes from Earth, it emits a flash of light every 6 minutes. These flashes are received on Earth every 12 minutes. Okay? And this is assuming basically a Lorentz factor of 2, which would require a certain percentage velocity to speed of light that you could solve using the equation for time dilation. During the hour of going away from Earth, a total of 10 flashes are emitted after the starting gun. Okay? If the ship departs from Earth at noon, clocks aboard the ship read 1 p.m. when the 10th flash is emitted. Okay? So there's the idea. So flashes sent from Earth at 6-minute intervals are seen at 12-minute intervals by the ship when it recedes and at 3-minute intervals when it approaches. So that means that in the Earth frame of reference, we have 120 minutes pass on the outgoing flashes. Okay? So there you have, right? There you have this, more time passes on Earth. Okay? Significantly more time on the outbound. On the way back, we have a reduction, only 30 minutes pass. Well, that means that in the Earth frame, if we take the 120 and the 30, we get a total of 150, right? So doubling and cutting in half give us a total of 150. Well, 150 is 2.5 hours, which is greater than the fixed rate aboard the ship, which is just 2 hours. So you see that it's about that asymmetry. We doubled it on the way out, we cut it in half on the way back, but when we sum them, we always get more time. Okay? Always. If there's a return trip, then the person will return younger than the person that stayed at rest the whole time. All right? All right. And this, you might have to go over this again for yourself, but make sure you understand it. Because, first of all, it's a great contradiction to the argument that relativity must be wrong because of the twin paradox, and it's fairly straightforward, okay? It just shows this idea about thinking about it outbound and inbound. And again, note that the Lorentz factor here is 2, which is why we double and cut in half respectively. Okay, so the ship sends equally spaced flashes every 6 minutes while approaching the receiver at constant speed. How will these flashes be spaced when they encounter the receiver? All right, they will be equally spaced with some value less than 6 minutes apart. You'd have to know the Lorentz factor. And again, in the example before, we assumed it was 2, and it could be any amount depending on how fast they're going relative to the speed of light. Okay, so since motion is relative, can't we say as well that the spaceship is at rest and the Earth moves, in which case the twin on the spaceship ages more? No, because it's not symmetric. Okay? Again, to say it again, the person on the planet only experienced 1 reference frame. The person in the spaceship experienced 2. That they're very different systems. Okay? Now, one thing that would make this impractical to actually do in real life is the amount of energy it would take to accelerate, decelerate the traveling twin, have them turn around, and then reaccelerate them up to an appreciable speed of light, and then decelerate again. It would just be too much energy. Okay, so let's think about the addition of velocities. We've seen relative velocities before, right? So if I'm traveling in a car at 60 meters per second relative to the side of the road, and I shoot a bullet at 300 meters per second relative to the car, then the bullet is traveling 360 meters per second relative to the ground, because they simply sum together, okay? That's relative velocities. That's often called Galilean relativity, okay? But Einstein realized that another consequence of his postulates was that relative velocities would have to be recalculated. And here we have Einstein relative velocity addition. Okay, so this is the equation for adding relative velocities. And what this equation allows for is that no matter what the relative velocities between 2 frames of reference are, light moving at c in one reference frame will always be moving at c in any other reference frame. And that means that you can never catch up to light. In other words, you can never say, oh, I'm in a rocket ship traveling at 99% of the speed of light, and then I fire a torpedo, a space torpedo, also at 99% of the speed of light. Well, okay, well, I got 0.99 plus 0.99, that's going to be 1.81, right? No, it doesn't, okay? If you add those values together, you don't get 1.81, you don't get almost twice the speed of light, because you don't add them like this, you add them like this. And when you add your velocities, both of them say being 0.99 the speed of light, then you're going to get something that is just going to be basically 0.999 the speed of light. This equation works, okay? And this is part of what Einstein did, is he actually worked out the math and found the equations that matched his postulates. Okay, so the other big consequence, length contraction. Now, I want to make it clear that time dilation and length contraction are really two ways of thinking about the same thing. Because when we talked about the fact that the time must be running slower in the fast spaceship, and that was the way that light could take a longer path and do it but still do it at the same velocity, well, that required, that idea that time was stretched out, okay? It was running more slowly for the traveling person, okay? The faster person. Well, another way to think about it is the length is contracted, okay? So it turns out fast-moving objects have contracted length, okay? So as objects move through space as well as time changes, okay? Because it's just two sides of the same coin. So space is contracted, making the objects look shorter when they move by us at relativistic speeds, okay? So a really fast meter stick moving by this person would appear to be shorter. Maybe it's only 30 centimeters long instead of a meter long. It is quite literally contracted, okay? And the equation for length contraction looks like this, where again we have the Lorentz factor. So it's L equals 1 over the Lorentz factor times the proper length. And the proper length is the length measured in the same reference frame as the moving object, okay? So the proper length of the meter stick would be 1 meter, and then the relativistic length is the length measured by the person that is not in the same reference frame as the moving object, okay? So in this case, it would be contracted, okay? So it's always shortened because the Lorentz factor is always greater than 1, okay? So length contraction takes place only in the direction of travel, all right? So that means that objects don't keep their same shape. They get squished. So we see in this case a spherical object getting squished until it's almost, when here it's moving at 99.9% of the speed of light, it's almost like just a line. And if it moves at the speed of light, well, actually that can't happen. We'll talk about that. Okay, so let's talk about it. Because one of the other consequences of this idea of relativity is then how much energy does it take, right? Because if you think about the relative velocity, you see that if you want to accelerate something, well, then that takes force. And then force times distance is work. And then, of course, work is energy. So then if you're bringing things up to close to the speed of light, then they're taking a lot of energy, right? And it turns out that it takes more and more energy the closer you get to the speed of light if you want to accelerate something that has mass, okay? So we see then that relativistic momentum just grows as we get closer and closer to the speed of light. Because, of course, the Lorentz factor is the 1 over the square root of 1 minus v squared over c squared. And so as we get closer and closer, as v gets closer and closer to c, gamma gets bigger and bigger, which means the momentum gets bigger and bigger. And to achieve that bigger and bigger momentum requires more and more energy, all right? So subatomic particles are routinely pushed to nearly the speed of light, 99.999% the speed of light. And it takes huge amounts of energy, even for the small mass of those particles. Classically, the particles behave as if their masses increase with speed. So sometimes you will see relativistic mass, but that's a bit of a confusing way of saying it. It's better to say relativistic momentum. The increased momentum of the high-speed particles is evident in their increased stiffness of the trajectory. They behave as if they're bigger, okay? The more momentum it has, the stiffer its trajectory. It's harder to turn it, right? So you think about a large mass object, okay, like a big mass, it's going to take a big wide turn, and then a small mass object is going to take a very tight turn, okay? If you recall, that was the exact premise behind the alpha particles and beta particles in cloud chambers and bubble chambers, right? We can see their different trajectories, okay? So same idea here. But here we actually have the same particle, but when it's moving bigger, or when it's moving faster, it acts like it's bigger. Because it really is. It really does have more energy, okay? So if the momentum of the electrons were equal to the Newtonian value, all right, the beam would follow the dashed line shown here, okay? But it doesn't. The relativistic momentum of them using gamma mv is greater. The beam follows the stiffer trajectory. So this is experimental evidence that electrons at high speed behave in relativistic ways. They have relativistic momentum. They act as if they're more massive, okay? So a piece of matter, even at rest and not interacting with anything else, has an energy of existing, okay? This is called its rest energy. And this rest energy is just an amazing idea that Einstein arrived at when he was calculating the relativistic momentum, because he found that it took an infinite amount of energy to raise something with mass to the speed of light, thus it's impossible. And that really kind of made him question what it means to have mass and energy. And he realized then that mass and energy must be themselves interchangeable, and thus things that have mass are truly just a form of congealed energy, okay? So Einstein concluded that it takes energy to make mass, and then energy is released if mass disappears. So again, let's just stop and appreciate this, because this of course led to nuclear physics, led to the creation of the Manhattan Project and the nuclear bomb. And it just came from asking yourself, if speed of light is the constant of the universe, what is the consequence of that? It's amazing that one thing can lead to another, okay? It's just mind-boggling. And of course, the huge amount of energy included in mass is now, it's both a something to fear, but also something to wonder about the potential of, okay? So the amount of energy E is related to the amount of mass is the most celebrated equation of the 20th century. And it is an equation from special relativity from the two postulates that we started this lecture with. It follows literally from those two postulates, and other than that, just classical physics, okay? So saying that a power plant delivers 90 million megajoules of energy to its consumers is equivalent to saying that it delivers 1 gram of energy to its consumers, okay? 1 gram is equivalent to 90 million megajoules, all right? In 1 second, 4.5 million tons of mass are converted to radiant energy in the sun, okay? That the sun is turning matter into energy. The sun is so massive, however, that in 1 million years, only 1/10,000,000th of the sun's mass will have been converted to radiant energy, okay? So, finally, let's finish things off with the correspondence principle. Well, this is a principle that states that any new theory or any new description of nature must agree with the old theories. So if the equations of special relativity are valid, they must correspond to those of classical mechanics, like Newtonian mechanics, like Maxwell's equations. All right, when the speeds are much less than the speed of light. When speeds are very low compared to the speeds of light, v is much smaller than c. And so we get that the gamma factor quickly approaches 1. All right, and it's so close to 1 that even the most sensitive measurements for things that are moving at, say, speeds of 1,000 meters per second will not measure relativistic effects. Okay, you have to be moving at tens of thousands of meters per second at least, okay, relative to another reference frame. All right, so in summary, here is relativistic time, right, which for very small v's simplifies between the relativistic time being equal to the proper time. Relativistic length for small values of v shows that the relativistic length simplifies to the proper length, all right? And for relativistic momentum, we see that relativistic momentum just simplifies to classical momentum mv for small values of v, okay? And by small, again, just to stress this, I mean anything less than 10,000 meters per second. Okay, well, there we have it. I hope this has been a very interesting lecture. I think this is amazing stuff to think about on special relativity, Einstein's first theory, okay, and historically, and a just watershed moment for modern physics. In our next and final lecture, we'll talk about general relativity, Einstein's much broader, encompassing, and more difficult to understand theory about acceleration and reference frames. Well, thank you so much for watching this lecture. I hope it has been interesting and informative.